So thanks, Matt, very much, and thanks, Andy, as well. For the final session for this morning, we have David from SCI Semiconductor, where he's a Director of System Architecture. So please join me in welcoming David.
Great, thank you very much. So we're at an open source conference, so I wanted to start by saying everything that I'm talking about today, including the core that we're going to be taping out later this year, the RTOS that we've built on top of that, the tool chain that lets you take off-the-shelf C and C++ code and compile it for a memory-safe target, and even the formal specification for our RISC-V extension are all open source. So we've probably all seen this joke, and it's an old joke, and we keep seeing it because it keeps being true. And it would sort of be understandable if the kind of things we were talking about were, you know, some fly-by-night company is set up, ships a device, goes out of business, and stops shipping updates and their device is insecure. But this kind of vulnerability happens to major consumer electronics companies. It happens to devices that come from the world's largest cloud provider. It happens in real-time operating systems shipped on 1 billion devices backed by the world's largest software vendor. And, you know, this last one is a remote code execution vulnerability in the network stack that allows total compromise of any device shipped on that system. And really the root of this problem is the hardware that you're trying to build on is incredibly cost sensitive. You know, cents, pennies on the total hardware bill of materials for an IoT device can be the difference between you sell 10 million of them or you completely fail in the market. And this means memory is really constrained. We're talking about things with, at the low end, tens, at the high end, hundreds of kilobytes of memory. And that's not enough to run a rich managed language that gives you type safety guarantees. There are no mitigations in the hardware. If you look at larger systems, mobile phones on up, you look at things like OpenSSH, you look at things like Chromium, they use different processes to isolate different security contexts, and that relies on an operating system with processes as an abstraction, and that relies on an MMU. If you look at the size in terms of transistors of an MMU, it's larger than most embedded microcontrollers. So there's no space for that. And at best, you have a memory protection unit, which is the sort of thing that you'd design if you're a hardware person who really, really hates software people and wants to consume energy and give you an abstraction that is basically impossible to use. So this is the sort of problem space that we're looking at. How did we get here? And it's been a long path, and I guess if you go back to historical capability systems, it starts in the 60s, but I only have half an hour and you're all eager for lunch, so I won't go all the way there. In 2010, DARPA put out a call which was fantastic, saying, if you could change anything you like in the hardware-software stack to improve security, what would you do? And so Cambridge and SRI International put in a proposal for the CHERioT architecture, which took some of the ideas from historical capability systems, some of the things that have been learned over the subsequent 50 years, and built something that was adapted to how modern superscalar, deeply pipelined processors work. And how many people, by the way, saw the glibc vulnerability that allowed local code execution this week? So if you haven't patched that, good idea too. If you're running on a Cherry system, it's not exploitable, it's fine, you can ignore it. Cherry's had about 200 million in investment so far. A big part of that has been ARM producing a test chip for server-class hardware. If you want to go and play with one of those, there's one just downstairs on the FreeBSD Foundation stand next to the Digital Security by Design stand, which has been managing the UK investment in that overall program. I joined this project in 2012, so I'm a relative newcomer. One of the things that was really fantastic, and the reason that Cherry was able to succeed where a lot of other places have failed, was the breadth and diversity of experience. So I was leading the programming languages and compilers strand of that research, but there were also experts in hardware, in security, in operating systems, and so we were able to adapt things at whichever layer of the stack they needed to be adapted to be able to get the security benefits. And in 2020, I was leading a team at Microsoft that was looking at how we could use these at the sort of scale that Azure cares about, which is 128 core machines with a terabyte of RAM. And we started thinking about what happens if we go in the exact opposite direction. If we try and scale everything right down to the smallest possible devices. And Microsoft had a product based on a chip that a partner MediaTek fabricated called Azure Sphere. And it ran Linux to give you a secure update service on one core, and it gave you a microcontroller core, and it gave you a hardware root of trust. And it gave you some quite nice security properties, but it was really expensive for the market segment. So our starting point was, can we get better security properties than Azure Sphere has in less than 1/10 of the hardware if we build on top of Cherry as a starting point? And I want to shout out to Hongyang Zaya, who was on my team there as a postdoc. It would be an exaggeration to say he single-handedly built the first prototype, but only a small one. And this adapted a lot of the work we've been doing on temporal safety for large systems. The trade-off space is very different when you're trying to do temporal safety on a terabyte heap to a 64 kilobyte heap. And in early 2023, we open sourced this to get some external collaborations. A lot of that has been on formal verification. The University of Oxford has been doing amazing work formally verifying the IBEX core. And so once we got the prototype, we engaged with one of the product groups inside Microsoft, and they said, hey, we need some microcontrollers for our larger SoCs, and a bunch of those were the kind of things they build were announced recently. Do you have any ideas about how we could do a secure one? And we said, yes. Talk to us a lot more. And they ended up building the production quality implementation, which is what's been open sourced. And that's what Oxford's been verifying. We've also been collaborating with some folks at Google who have been looking at verifying the core of the TCB for our software stack. And all of that is enabled by having a formal specification of our RISC-V extension. And so we're able to formally verify security properties right from here is some C-level abstraction to and here are some gates. And then there's physics underneath, and that breaks everything. But if you ignore the physics, everything is fine. In late 2023, I moved to SCI, which is a new startup that wants to produce chips built on top of this technology. Microsoft, they had some internal use cases, but Microsoft fundamentally is not a microcontroller vendor. And Microsoft does not want to be a microcontroller vendor. They will happily sell a lot of services to people who buy microcontrollers. But SCI wants to actually sell you chips. And more recently, Low Risk, who gave a talk this morning, yesterday, has been building a rich FPGA prototyping platform that you can use with the CHERIoT platform. So what do we give you, and how does it actually work? Well, at the very foundation, we get a lot of guarantees that many of them are shared with any Cherry platform, and a few are things that we've somewhat refined. You can't inject pointers. There's no way of saying, oh, I know the memory address of this thing, so I'm going to forge a pointer, and now I can access this bit of memory. That just can't happen. There's no way of doing out-of-bounds accesses, and there's no way of exploiting use after free vulnerabilities. So that Azure RTOS vulnerability from December, that was a combination of an out-of-bounds write and a use after free. So if you had exactly the same software running on our platform, and you still had that vulnerability, the first step in your exploit chain would cause you to trap. And if you're building a safety-critical system and something in your network stack causes your device to crash, that's actually bad. So the next step around that is because we have this fine-grained memory safety, we can use that as a building block for compartmentalization. And that lets us really reduce the blast radius of this kind of thing. So your network stack crashes, okay, now you've lost your connection to your back-end service. You need to restart your network stack, reestablish your connections, but your real-time control loop is totally fine and unaffected. And the crash happens before the memory corruption, not afterwards. It's not like, oh dear, you've overwritten an arbitrary chunk of your heap, and now you're on the next page, so you get a seg fault, and hooray, you're in an undefined state, but you can try recovering, good luck. We'll give you an error handler that you can run just before the memory corruption would have happened. And that's as far as we go at the system level, but then at the operational level, when you assemble a firmware image on this platform, we can tell you all of the interactions between components, we can tell you what all the rights are, and so you can build rich policy enforcement of the kind that will enable you to support things like right to repair legislation and safety critical regulatory compliance. So being able to say, I have this bit of code that the regulator has signed off on. This is the only thing that is allowed to talk to this physical device. But if the user wants to rip out my cloud service backend and plug in something that talks to Home Assistant or whatever, totally fine. We can still sign their firmware image because it complies with the policy that enforces the safety critical invariants. And all of this is really in service of two security principles. And if anyone is trying to sell you any security technology, ask them how they respect these two principles. And if they can't tell you the answer, they're selling snake oil. Principle of least privilege people talk about quite a lot. It really says, if you don't need a right, you shouldn't have that right. And that's great, but it requires you to have a way of expressing rights, and it requires you to have a way of expressing a boundary around the thing that holds those rights. And so for us, the rights can be as fine-grained as you may read this one byte of memory. And the granularity of a compartment can be as small as this one function that has this one global that maintains some state. Something as simple as a monotonic counter could be a separate compartment. The other principle that pairs with that is intentionality, and this has been, violations of this have been the root cause of a lot of vulnerabilities. There was a really high-profile one in Exchange a couple of years ago because Exchange had the ability to write anywhere on the file system, but you could trick it into exercising that right for something that actually should have been constrained to a particular directory. And again, if we're talking about things like memory, this is really enforced right down at the hardware level. Every load instruction, every store instruction, every jump instruction must have as one of its operands a valid pointer that conveys the correct rights to do that operation. But it also surfaces higher up in our software stack. If you want to establish a network connection, you have to present the authorizing capability that says, I am allowed to connect to this network server. And so we can really enforce very fine-grained, auditable privilege separation and intentionality. So I've sort of talked a lot in the abstract so far. I want to give you just a little snippet of code. So this is something that allocates some memory on the heap. Heap allocate is the low-level function that malloc is just a wrapper around, which will do an unlimited timeout and will pass a default capability. This returns a pointer, so we're going to print that, then we're going to free the pointer, print it again, and then we'll take a look at what that malloc capability that authorized this operation was. So when we print this thing, we see it's a cherry system, so a pointer isn't just an address, it's an address and a load of metadata. And the address is just as it would be on any other system. It's a microcontroller, so it's a 32-bit address. But then the next thing that we print is a non-addressable tag bit, so you can't write to these in memory. This is really an attestation from the hardware that says, I promise that a set of rules have been followed that ensure that this is something that has been safely derived from other things. So when you boot up, your system has a few capabilities in its registers that authorize access to everything. when we start the memory allocator running, it has a capability that authorizes access to the whole heap. When you allocate memory, it will give you back this constrained capability that authorizes access to a specific object, and not, importantly, access to the object header that contains the metadata that the allocator is using. And that's bounded. It has a range which we can express as either a base and a top or a length. They're densely encoded and compressed, but we expand them and print both for debugging because sometimes it's useful to see one, sometimes it's useful to see the other. And it also has a rich set of permissions. So we print these in groups with uppercase letters for the higher order ones and lowercase letters for derived permissions. Here, G means it's global, and that means you can store this anywhere. If you remove that permission, you can only store it on your stack. And so you can use this to enforce cross-compartment stack temporal safety or scope delegation, where you say, I'm going to hand you a pointer, you can access this object, but only for the duration of this call. And when you return, you know that that hasn't been captured. The next two are fairly self-explanatory. Read and write, you can load and store via this pointer. And then we have some that compose with those two. So C for capabilities, you can load and store pointers. If you remove that, you have a data buffer. You can load and store data, but you can't store pointers into it. So that lets you know it's not being used as a covert channel for smuggling access to other objects. Permit load global, which is slightly complicated, means it's sort of the transitive version of the global permission. If you remove this, then not just can you not capture this pointer, you can't capture any pointer that's reachable from this. So I can hand you a pointer to the root object in a really complex object graph. You can do as much pointer chasing as you want, but you can't capture any of the pointers that you reach. You can store them on your stack, you can have them in registers, but you can't put them on the heap or in globals. And M is the equivalent of that for the store permission. So if you remove that, now you have deep immutability. And this combination of things lets you have really rich interactions between compartments. So then we call free, and I won't make you play spot the difference on what's changed from one line to the next. It's really just this one bit. The hardware guarantees that after you've called free, any existing pointers that you have to the freed object will now not be valid. And that means if you use them in loads or stores or jumps or any instruction, you'll get a trap. And so that use after free that was so embarrassing for Azure RTOS is deterministically mitigated. That problem can't arise. The last thing I wanted to mention here is that malloc capability. And this is different from the two lines above in that the object type, which I haven't talked about yet, is not zero. And a non-zero type for a pointer means it's sealed. And if you have a sealed pointer, the only thing you can do with it is unseal. If you try and dereference it, if you try and jump to it, well, some of the sealing types are used for sentries where when you jump to them, they're implicitly unsealed, and you can use those for enforcing control flow integrity. But some are reserved for software use, and that's what we use to give you these opaque tokens that in the compartment that holds the capability that allows you to unseal them are just pointers to objects once you've unsealed them, but with really strong tamper-proof guarantees. So you know when you unseal one of these, it really is a pointer to allocation state. And so this object will encapsulate a quota, and this is how you guarantee that your compartment can only allocate a certain amount of memory. You can't, via any mechanism, tamper with the internal state of that object. You can just pass around that as if it's a handle. And the last talk talked for a really long time about SBOMs. And SBOMs are great. You know, they tell you where your code came from, but they also mentioned one of the problems, which is, okay, I have used this component, and it's got a vulnerability. How much damage can it do? Am I using those code paths? And so when you link a firmware image on this platform, you get, as well as the linked image, you get an enormous JSON document, which makes your SBOMs look very small in comparison, which tells you for every compartment what entry points does it export? What does it call in other compartments? What sealed objects does it have? What's their type? What's their contents? What does it call in other compartments? And so you can start to reason about, and you can build code signing policies that tell you, that only operate if you follow a set of rules for things like what's allowed to talk to the network stack, what's allowed to talk to this safety critical device, what is the identity of that, is there any reachable flow to a function that runs with interrupt disabled that is not on my explicit allow list of things that have bounded execution time. So I wanted to just finish up by going through a little bit of a worked example for a somewhat simplified version of our network stack and show how each of these properties goes together to give us something that has really strong end-to-end security properties. And this is because the kind of thing I want to be able to buy for IoT devices is the kind of thing that I can expect will last 10, 15 years. You know, if I buy a fridge, I don't want it to be obsolete in 5 years because now it's got a security vulnerability. But I do want my fridge to have network connectivity so that it can talk to my smart meter and so it can run the compressor more when electricity is cheap and less when it's expensive. You know, I want to have all of those energy efficiency benefits that you get from connectivity, but I don't want to have to replace all my devices every 3 or 4 years because that somewhat offsets all the other savings. So this is what happens if you remove all the TLS and other complexity from our network stack. The blue boxes are code that we've written from scratch. Each of those boxes in the bottom left are separate compartments. The orange boxes are almost entirely unmodified third-party code. So we've taken the FreeRTOS network stack, we've taken the FreeRTOS SNTP library, we've written some wrappers around them, but we haven't modified a single one of their source files. And that's really important because, you know, rewriting stuff in a safe language is such a waste of everyone's time. If you're writing new code today, please use the safest language you can for your target. You know, don't write new C code. There's just no excuse for that. But if there is already a solid battle-tested C library, and you rewrite that, that's a phenomenal opportunity cost. While your competitors are adding new features, you're embarking on a project where your goal is to reach feature parity with where you were yesterday. And so that's insane. And the FreeRTOS network stack is written in MISRA C. It has memory safety proofs. We only found one memory safety vulnerability when porting it, which is probably not exploitable, and annoyingly, they fixed it 2 weeks after the version that we had ingested. So we didn't even get to report it to them. But, you know, it's a huge piece of engineering, and I don't want to rewrite a network stack from scratch, and you shouldn't either unless you really like network stacks. Okay, so the green box is a placeholder for application code, the kind of thing that if you're building an IoT device, you would write yourself. And there's just one compartment here, but typically you'd have at least two, one that does the real-time control system bit, and one that does the internet monitoring control part. So inside that is one of these sealed capabilities that points to a statically sealed object which will show up in that linker report and so is then auditable at firmware link time. And this is a network connection capability. It says, I am allowed to make a connection on this port to this host using this protocol. And when you want to create a connection, you hand it to the network API compartment, and this is the thing that runs the control plane for the network stack. And it unseals it, and as part of unsealing, there's an implicit check that, is this really a thing of the type I think it is? And if it isn't, then unseal fails, you get back an invalid pointer, you check for that, you return an error. Or if you try and use it, you crash, so don't. And then this will open a hole in the firewall to allow a DNS request. So most of the time, we're not doing DNS requests, so we keep that closed in the firewall. And then it asks the network stack to look up the address and create a connection. So DNS request goes out, DNS request comes back, and we get the name lookup response, and we get the sealed connection object. The control plane compartment then closes the firewall hole, so anything that's spoofing the DNS server's source address now can't attack our network stack. It only has that very narrow 1 or 2 second window while we're waiting for the DNS response. And we hand back to your compartment another sealed capability which encapsulates the FreeRTOS network stack's socket object, the connection state and the send and receive buffers, and everything that's associated with that connection. And now that control plane compartment is out of the story. And when you want to send and receive data, you just pass that capability in the same place you'd pass a file descriptor if this were a Unix system. Our APIs are built around the idea that you have a shared heap, and so some of them are a bit easier to use than the ones where it's, oh, I have a buffer, I allocate a big buffer because I don't know how big the thing is. We can allocate on your behalf in this compartment because you can also pass your malloc capability in. And we can also transfer ownership for zero copy receive on UDP. This, again, unseals that capability. It knows that this really is a valid socket object as a result of that. It knows you have no ability to tamper with it. And so we've got that isolation that you'd normally have as a software engineering boundary now is a really hard security boundary. The firewall was already opened as a side effect of creating this connection object, and so we can send a request to example.com, we can get the response, and that can then be forwarded back to your application. So the on-device firewall I haven't really talked about very much, except that it's a thing, packets sometimes go through it, sometimes they don't. The reason it's important is twofold. First of all, if a malicious host sends you a packet, it just doesn't go through. And this means, even though we kind of like the FreeRTOS TCP/IP stack, if we can remove it from the attack surface, that's obviously better. And a thing that just matches on the 4 tuple in the packet header is much simpler than the network stack. And so we just stop a lot of packets ever reaching it. So this means if you're a remote attacker and you want to try and compromise the network stack, it's really hard to even send data to it. You have to spoof something coming from an endpoint that something beyond the network stack is authorized to talk to. But also, because it's in a separate trust domain, if it's compromised and it tries to join a bit botnet, does anyone remember the Mirai botnet from a few years ago where a bunch of IoT devices were all compromised and launched massive denial of service attacks on everyone else's? Yeah, so that's really embarrassing if you're a vendor and your device joins one of those things. If we assume that the FreeRTOS network stack has been completely compromised, and that's really hard because we break a lot of the primitives that you need for that kind of exploit. But it's a good rule of thumb for security to always assume that anything can be compromised. So ignoring all of the things we've done to make it very hard to compromise the system, if that is compromised, it still can't make arbitrary outbound connections. And if you contrast this with something like Linux or Windows, where your on-device firewall and your network stack are both in the kernel, if you compromise the network stack and you get arbitrary code execution, well, now you can just go and turn off the firewall. There's a very narrow interface between these two, which is really just pick packet, put packet. And so there's no access between these two for the control plane for opening and closing firewall holes. So to sum up, we've got the ability to take off-the-shelf existing C and C++, recompile them, and get really strong memory safety guarantees. We can then use that to build lightweight compartments. And the thing I always like to repeat is isolation is easy, safe sharing is hard. We know how to do completely isolated components. You just run them on different computers. But for things to be useful, they need to communicate. And so we have a rich set of primitives that allow you to communicate by just passing pointers to function arguments, but have guarantees like deep immutability, shallow immutability, deep no capture, shallow no capture, enforced at the hardware level. Once you've built that graph of compartments, you can get attestations over exactly what is linked, what communicates with what. And we're building all of this on an open source hardware and software foundation. And again, just to plug my employer, microcontrollers built on top of this should be available to buy in your favorite retailer at some point this year, to be announced. I'm aware it's lunchtime and we started 10 minutes late, we're finishing 10 minutes late, so I will stay here if anyone wants to ask questions, but I suggest anyone who doesn't goes and gets lunch. Anyone who's watching the recording or doesn't get to ask questions, if you go to the CHERIoT RTOS repo in the Microsoft org on GitHub, there's a discussions thing, there's a Q&A section, ask questions there. This QR code will take you there. Thank you.